Hi everybody. My name is Bar, and today I'm going to talk to you about a challenge that we have in the company that we work at, BRIA, of training a latent diffusion model from scratch. So this is me. In the last 8 years, I worked at an AI-driven company, enjoying solving problems. And people say I have too many hobbies, but I disagree. So just a little brief about BRIA, because it's important for the scale of the training and what we do. We're actually developing a generative AI infrastructure for developer or platform, a holistic platform. And what we do is we develop a foundation model, and we access them via the source code. We call it source available, and also APIs and SDKs. And what the research teams that we work with can get in the end is like a set of pre-trained model, like foundation model trained from scratch, and also the auxiliary models like supported LoRa, controllets, and again, the source codes and weights are provided for research teams in order for them to drive innovation and do developments on top of. And the unique angle of what we do is that all of the data that we received is fully licensed or legal. We have a data partnership with major data providers that gave us the full legal rights to use the data. And then we trained it, and this is why we trained them from scratch, meaning that the model didn't see never trademark stuff like Yoda, Superman, or like e-commerce stuff. Everything was provided by us legally, and then we trained it from scratch. And our unique commercial side of this aspect is that we give royalties back. So meaning that all of the data partners get royalties, let's say the Spotify model or Apple Music. If I upload my music and then someone listens to it, I get royalties back. And this gives them incentive to keep bringing me data, me to keep training the models, and the developers enjoy like a safe generative AI platform. So this is a bit about BRIA. So the diffusion process, which is like the core of our models and what we do. So a brief like bird view of diffusion. So a diffusion model in the areas of text to image, which is the majority of the models that we have today in BRIA, is a model that starts with some random noise. It doesn't know anything about the world. And then we guide the model via text. We provide it a text, and then there is like an optimization process. And eventually we get a visual according to the guidance that we give. And again, we developed BRIA also auxiliary models, so a control net, like I can give a sketch and a text, I can give several guidance, but mainly text. It's like the most foundational thing that the models see. And this process is very, very a long process. Like at inference time, it's very fast, but at learning time, there should be like a lot of data, like petabytes of data, hundreds of millions of images. And then this process, like, it's a very repetitive process. We repeat it like for weeks, and eventually we get the model. So it's like a very heavy load process. So to make it like more down to earth, I am going to play like a little game to demonstrate how this process looks like when two persons play that game. And there is me and my colleague from BRIA. We're going to play a game where Efrat, my colleague, is very expert at the task, and I don't nothing about the task. So we start by giving me a task to find an employee that works at a unicorn, and I found our CEO, and then I asked, is that correct? And she said, not yet. Hold on a bit, not yet, but try again. And then I try again, and I found this guy, Elon Musk, and then she said, okay, this is probably a good score. I give you a 9. If we're going to play this game for weeks with a lot of data, eventually I will be good at a task without Efrat learning, teaching me this task personally. And this procedure called a stochastic game. It's a principle from game theory, and basically the foundation model that we train is based around this concept, doing a lot of iteration, a lot of time on a lot of data, and eventually we can teach a model that was a dummy at a specific task to be very good at. So before we go into deep dive to what we did at BRIA, like back in time 4 years ago when we started, there was a model called StyleGun. A lot of startups started to use it. It was based on an article from NVIDIA. And StyleGAN was a model that was trained on a dataset called Celeb A. It was 200 images-ish. And to train it, we had to use like a single machine with 8 cards, NVIDIA Tesla V100. And it was trained for hours to maximum of 6 days if I like to train it from scratch. And then we were able to do inference. So this was BRIA 4 years ago. This is what we started with. But since then, like technology and the architecture of these models became a bit more advanced. So today, fast forwarding 4 years, this is how our stack currently look like. So we build a sort of a supercomputer on top of AWS, which composed of an orchestration unit and then a set of 128 machine at max of NVIDIA A100, and also like a data layer where we ingest petabytes of data to the cluster, and then there is like a evaluation process, which I'm not going to mention today, but it's like a very interesting evaluation process that involves some interesting psychologies mechanism. So I'm going to start with the data layer. We're going to break down this infrastructure and see the challenges that we had and how we tackled each one. So first of all, the data layer, as I mentioned, like hundreds of millions and petabytes of data. So basically, like if we put it on a graph, this is how training looks today at BRIA. So I'm from the research team. I like to start an experiment. To spin up the cluster, the compute layer, it takes around 5 to 8 minutes. And then I would like to immediately get started with the training. I don't like anything in the middle. I like to start utilizing the GPUs and see results. So this is more like a demand. It's not a solution, but it was a demand that we had to tackle with. And also the throughput of the experiment works like if I have experiment number A, and then I can pause for days, weeks, maybe I do a product evaluation, maybe I have bad results. It can be a lot of cases where I just stop for days, weeks, or months, and then I do another short experiment, and then I wait again, and then I do a huge experiment that should solve all my problem, and then it crashes, and then I'm stopping for evaluation, and a lot of stuff happening in the middle. So eventually, how we work is like it's in blips. We scale it up and scale it down, and it's not like recurrent. It's not like maybe university where I buy a huge cluster and there is a queue, and all researchers in the university just fire experiments and wait in line, and GPU works all year, 100% utilization. So this is another challenge, and again, cost-wise even, that we had to deal with. And last one for the data layer, it's like petabytes of data. It's a lot of data, again, hundreds of millions, and we had to digest them to the clusters for weeks, 2 or even more sometimes, and it's like a long and painful process. So in the data layer, eventually the solution that we came up with is that, first of all, we took this huge amount of data files and compact them to a small files for 5 gigabyte-ish, and then we just save them in a bucket, and then we connect them to the cluster via a feature called FFM, which is fast file mode, meaning that when the cluster needs an image, it doesn't need to preload it, it just fetches it immediately, like in real time. And this means that instead of opening hundreds of millions of connections, we opened less connection that we need, and just utilizing the benefits of the cloud of bandwidth in opposed to just opening a lot of connections. And the second thing is that this huge cluster of machine, when you do a distributed training, when I'm going to deep dive a bit further down this track, all of the GPUs to do the iteration part that I mentioned have to sync. Every time that we calculate the gradients and eventually see a big batch of data, we need to pause, we need to say, yes, everyone is synced, calculate the loss, and then continue to the next iteration. And it's a very, very long process. And in that process, if I worked serially, where each GPU said, okay, I'm working on this chunk of that data, doing my calculation, and then going like that to the next one, it was causing a really bad bottleneck, because each GPU had to wait to his adjacent GPU, and it was taking, it shouldn't be like that, and it will take a lot of time to converge. So what we did a divide and conquer. Like we used the data loader when we passed a fixed seed, and then each GPU get a colored, a chunk or a shard of the data, and then he knows that for the entire life cycle of the experiment, he's going to work only on that shard, and also if the training was stopped, then we spun up the cluster and he continued to working on the same shards, meaning that there is no continuing in the same way it was before, so it was less biased because you are averaging a huge batch, effective batch in the training. If each time different GPUs saw different data, it could have like converged to a different way. So it's smarter to have a fixed seed. And then this ensures us that every GPU just work on his chunk of data, and then the communication was like an epsilon because each one started at the same time and approximately finished at the same time and continued to the next iteration. So doing these two stuff very help us to push the experiment faster and digest the data much more smoothly. Next is the compute layer. So as I mentioned at the beginning, we built like a supercomputer. We had to make all the GPUs work together seamlessly. It's like, imagine that if each one of the GPU was in a different data center or maybe in a different room, it causes a lot of problem because of communication. So first of all, we had to make sure, in help with Amazon and infrastructure, that all of the GPU, all the racks, sit in the same physical location, in the same room, close to each other, and to make sure that we bundle every rack together. And then each one of the GPU had to be enabled a feature of NVIDIA called NVLink, meaning that the data, the gradient that we calculate, the backpropagation, everything is done via high throughput connection, meaning not over the internet when they exchange gradient and then doing the work. And all of this was critical, we call it a supercomputer. It's critical to push the experiment and to converge fast. Eventually, if it will take like 2 months to converge, it's possible, but it will cost a lot of money. So we're aiming to converge fast and not have bottlenecks for bandwidth or any kind of this stuff. So this was the challenge of the compute layer. And again, we did it via SageMaker, which is a managed solution that helps us to wire everything to do it like that. Next thing is the network layer. A very important aspect because, as I mentioned, each GPU is talking to his neighbor. We had to enable a feature, again, that AWS support, that enable us this communication. It's a protocol developed by NVIDIA called NCCL. And just like if you're going to do a track like that, just make sure that your cloud provider enable this feature because it's a killer. If this optimization is not working, all of the communication will be slow and then all of your infrastructure will go to waste. So last thing is the code layer. I'm going to show like a brief code example. But before that, we build our training loop, actually. We started with a vanilla training loop for stable diffusion that's available on Hugging Face. You yourself can download it and train tomorrow a model same as the one that we did, the vanilla one that we did, which was pretty good. Since then, we changed a bit the code, but again, a valid training loop are available out there as an open source. So we use, in our training loop, Accelerate and PyTorch. Accelerate basically is a wrapper around the PyTorch distributed training, and it helps us by abstracting a lot of the stuff and not creating a lot of boilerplate code ourselves, which I show briefly. And then we use the policy called DDP, Distributed Data Parallel, meaning that each time that we program, every GPU get a copy of the training loop code, and as I mentioned before, work as a standalone unit, as a divide and conquer approach. So as developers, when we develop this stuff and even customize the training code, these are stuff that we need to take into account when developing distributedly, because it's not like the style gun approach where we had like a single machine with maybe tops 4 cards. And lastly is FSDP, which is a very optimized way when working in distributed training, and also very, very hard to scale even when you have 128 cards, and to scale it, it's very, very hard, as I will show briefly, if you're not using this optimization policy. So this is a very code snippet that I took, and again, the full code is open source on Hugging Face. You can search for stable diffusion code and see the full code, but I just took the main parts and I'm going to try to bind it to the infrastructure that you see. So first line is the accelerate. We just import the accelerate, and then we get everything under the hood that we need to start the training. And then you see that the second line is configuring the FSDP. So if someone familiar with training LLMs or training other type of model that are not image, text to image, there is a lot of complexity when you start working distributedly. Sometimes the model is not fitting into a single GPU. You have like 80 gigs from NVIDIA, and the model is very large. You have billions of parameters. It's not fitting. Sometimes a batch, you need an effective batch of really, really huge amount of data, and it cannot fit into 80 cards. You need 2,000 cards, you need 100 cards. So there's a lot of problem of sometimes engineering problems if you cannot you have like an upper limit. If you cannot use more than 80 gigs, you have nothing to do. And if you cannot fit effective batch, you will need just a huge amount of machines and then pay for it. So it's two major pains. In our use case, the pain was not fitting the model to a single GPU. It was supporting the effective batch. We had to upload images that are very large, 2K images on a cluster of GPUs, and get an effective batch was very large. So what we did, we used the FSDP, which mainly, you can see in the first line, it have optimization offload to CPU, meaning that in the process of the gradient descent, in the process of the training loop, when you don't need the model on the GPU, it's being offloaded to the CPU, and then you save resources and GPU memory. And the other thing is like sharding the gradients. In the process, when you're doing the training loops, if a single GPU will work on all the gradients, it will not have capacity. We will fill in our resolution. A single GPU will be filled entirely if we give him one image. So one image on a single GPU multiplied by 128, we get the effective batch size, but it's not good enough for us. We need more than a single image per GPU. So what FSDP is offered is that each GPU will shard the model parameters, the gradients of the model, and each GPU will get its own little chunk of calculation. And then once it's finished, they will communicate and say to all others, I did your part, here is your part that I did, and the rest will do the same, and then they will converge. Meaning that each GPU is doing less work, more GPU capacity is available, and we can scale the batch even forward, and then it eventually will cause a linear scale. If we need to have a bigger batch size, if the business said, you now need to support 4K images, we will not need to exponentially increase the amount of compute. We'll just add like linearly, we'll grow the compute as the resolution gets bigger, and again, will cause a faster convergence time and less cost. And the other part that I mentioned is the DDP. So in this simple, naive line of code, there is a with statement, and then accelerate, accumulate. Once this code gets entered, all of the code below it is copied to a different machine. So with this single line of code, this is you're looking at it as a singleton, but behind the scene, this line of code will copy all of your code across GPUs, and then accelerate give like very simple if statement that you can say, if sync gradient, if the operation of sync gradient is happening right now, do something. If I'm the main process right now, if this piece of code is the main process because all of the GPUs were finished and you like to log something or anything else, this is the place to do it. So there are several ifs that you can do to know where you are in this huge chunk of supercomputer with a lot of GPUs. So using these three simple chunks will get or understanding them will help you like to program better on a distributed training area. And eventually, again, this line of code also trigger the use of the network layer, which is the NCCL protocol, again, to communicate between everyone. But again, they accelerate, really abstracted everything for you without need. If you're using like a bare metal or a vanilla diffuse PyTorch code, it was significantly more line of code than this. So eventually, after we finished our first training, this is like weights and biases results from the first training that we did. So on the top, you see the GPU usage. Each color of the graph is a consolidation of X amount of GPU. And again, at peak, we use 128 GPUs. And you can see that the majority of the time, they're on 100% utilization. Sometimes you can see the drops, but this is the drops where we save checkpoints in order to evaluate, in order to see that we are on the right track. 2 weeks of training is very sensitive and costly. We like to observe, result everything, and if we are diversing from consolidating or the results are very garbage, you like to stop and not waste like hundreds of thousands of dollars per experiment. So we keep a close eye on the experiment all the time. And then you can see below, it's like the average batch time, the iterative process that we do a lot of time, which is 3 seconds. And for this resolution that we did in this experiment, it's like an industry standard, 3 seconds. It also helps us to calculate cost if I need to run in 3 seconds per iteration. And this is like step 1 million, sorry. So I know that 1 million iteration multiplied by 3 seconds, multiply the amount of machine cost per hour. I can predict very easily how much and go to the business and said, yeah, this experiment will cost X and this experiment will cost Y. So it's also very important that it will be stable and not picky like the GPU. So things we learn around setting up this infrastructure and doing this. It took us like several months. It was not easy. It was a lot to do with a dedicated team. So first of all, patience. Like things go wrong very occasionally, and there is ups and downs, and it costs a lot of money and a lot of pressure. So working on this infrastructure for months and failing constantly requires some sort of patience. It's very important to have a mindset where you're constantly failing. It's an environment you're always failing until it's like reaching a plateau, and then you're happy with the results. Second thing is to fail fast. If I shutting down the cluster, if something crashes, and then it takes me to spin up 40 minutes, which we had it back in the time until we did the ingesting via the FFM that I showed you. It will not yield a good dev velocity. You will get stuck. You will not be able to proceed. Everybody will be frustrated, and nobody will be patient. And this second thing is like there is like a very low supply of GPUs, and it's not that like we committed to an X amount of GPU and we know that you are going to utilize them. So eventually we are at the grace of the economy of the GPUs that is very poor right now. Everyone wants to train on A100. Everyone wants to train on the best and greatest and latest GPUs. And sometimes we wake up in the morning and said, this is an experiment I like to fire, and there is no GPUs. So the infrastructure should be very agile to move regions, to move around, and to be able to find compute wherever is needed. And you will need to be, again, the data should be moved across regions, and you need to be really agile if you like to consolidate in a reasonable time, because even if you started an experiment and you found out that on Sundays there is all the United States are not doing experiments, and then you start your experiment on Sunday, and later at Sunday or at night it crashes because of memory issue, you come out the next morning, you say, okay, I fixed that, I'm firing the experiments, no compute. So we can be stuck for 2 or 3 days without compute. So it's very important that the infrastructure will support and be agile. Optimize later. At the beginning, we thought, wow, these experiments are super expensive, a lot of money, and the business is pushing. Let's do optimization. While we are developing this infrastructure, if a GPU is doing something that is not optimizing a model, because the stable diffusion, if you know the architecture, have several inferences to train the model. The textual part, there is an LLM behind the scenes. There is a perceptual part, which is the unit. And not all of them are going through optimization process. So freeze it, do it pre-compute, and then save the data. And there is several optimization for the attention layer, which is a very costly mathematical operation that we thought about optimizing. And then once we started to optimize and develop and failing, we saw that we don't have capacity to optimize. We will need to bear with it, to pay extra for the experiments, but optimize later. It was simply, we didn't have the attention to do everything at once. Another thing is to do like a micro evaluation, if you say, and one change at a time, meaning that until I see that something gets wrong, and even if it's like a small thing that I did, and I think, it doesn't relevant, it's just a small thing that I fixed, until I spin up the cluster, go through steps, start pulling data, it can also be a pain. So what we did is we had like a very small data set that we can converge in 1 hour. ImageNet, it's an academia data set that was proven, and a lot of guys trained the diffusion model on top. And each time we did an experiment, we just ran this ImageNet, saw the results, make sure that everything is correct, and then we did it chainly, one after another, and then we did integration, everything together. And if it's ImageNet also, it's a very easy data set of animal, nature, stuff like that. So we were accustomed to look at the results, and we know what to expect. It was very easy and only take 1 hour. So every change that we did a micro evaluation, continued, and then did the integration before releasing a big experiment. It was very productive and assuring that we started to do that. And last part, I know that HR doesn't like it, but try to be negative as long as possible. If you wake up in the morning and everything works okay and the cluster is up and there, question everything. Everything doesn't work okay, everything is bad, and you should take 4 people from the company and look at weights and biases and try to think what is wrong, even if it's all wrong. And it's really helped us to find the unknowns, things that we didn't know what to expect. And by looking at the data and looking at the graphs and looking at the evaluations, sometimes, not always, but like 30% of the cases, we did find stuff that are interested and also that make us to like kill the experiment and said we need to rethink it. So after a lot of work, today we have like 30 models. If you like, you can go to Hugging Face, there are demos. The models themselves are not open because there are all the attribution part that I mentioned. You can ask for access, and we have like the startup and the academia and all sort of plans if you like to actually get the weights and do something with them. But anyway, if you just like to play around, we have a lot of demos for all of the models. So I encourage you to go to and have a look. And that's it. Thank you. If you'd like to be in touch. Sure.
So we obviously use GPUs a lot, not only for the sort of experiments, but also in production, right?
Yeah.
Doesn't it make sense to commit for a longer period of time and just receive what you need, and then distribute in your own way between the experiments and the production?
Yeah. So the question was, if you use a lot of GPUs on the training part, it makes sense that you also use it on the inference part, on production. So it will make sense to like obligate to a certain amount of GPUs, and you will probably use them if it's production or dividing the load or something like that, right? So basically the product is mainly, we're not serving it as an API mainly. We have like demo that you can use in our site that run these models, and we have like on peak time 10 GPUs, but the GPU that you need in the inference is significantly lower than the GPU. We use NVIDIA A10, which is G5 on AWS. It's a very cheap GPU that costs $1 per hour and is not capable at all to train diffusion models. And also it doesn't support the NVLink. If you have like a machine that have eight of them, they don't support NVLink. They don't have enough capacity. They're not strong enough to do the diffusion part. So again, 10 at tops we use in production. So even if we had the A100 or G100 or B100 that came up recently by NVIDIA, it's not the same scale.
Okay, so I'll rephrase my question. The experiments are recurrent, right? You continue to develop and you will always do experiments. So doesn't it make sense to still have to commit to a certain amount, having that you always do experiments? It's your business.
Yeah, but let's say, imagine, so the question was like, if I do it recurrently, the training, so at least I can estimate, like predict when I will need the GPUs. But the fact is that when you commit like for a full 1 year, 3 years, 2 years. So in that time, if I have like a month, then I do a pivot in the training or something off, I pay for a month for a cluster of 128 machines. So this month will not return itself. It will just me paying for a cluster that I don't use. And again, a month without utilizing a cluster, it's like a $1 million. It's like a lot, and I didn't do anything. So, and the fact that also our training are pretty random. It can be 2 trainings in a single month, and then it can be, again, months, like 2-3 months that I don't do anything, and I just implement, like now, a new architecture. There is a new architecture, like stable diffusion 3, and then we saw the architecture. It supports text alignment. They switch the encoder under the hood, support more tokens at the textual level. So it's like a research that has been going for 4 months, and we don't train anything in these 4 months. So it's like, I cannot commit. I don't know. This market is like so ups and downs, and every day new stuff coming up, and I cannot commit. I just cannot commit.